Alright, so yeah, my bad. The last few videos had no audio, so thank you for pointing that out to me. And I've got my audio working now, and I've got a wireless mic on the way. I don't know what went wrong. I tried it this morning and it wasn't working, and I tried it again and it started working. So I really don't know, but it's just one of those mysteries of computers. So hopefully these will all have video. So on the Canvas page, there's a link up there for shared code. Occasionally I'll post pieces of code up there that we've gone over in class that I think might be useful for you to have. So this is just a link to a public area on the Linux server, so linuxengrcs.com, to Linux shared, and come down under 222. So this was the file we were playing with yesterday to create 100 nodes in a linked list. So I'll throw things up there occasionally if they seem useful. I'm not responsible for whatever else you may find here because I use this for other things. But if you want to play with hex bugs, you can find those under Mesa.
That code you showed us, were you not freeing the memory?
Say what?
I don't think you were freeing the memory in that code you showed us.
I wasn't referring to memory?
Freeing it.
Oh, no, I wasn't.
Yeah.
Big memory leak. Alright, so that's available up on Canvas. So, any questions so far? ODP 207, okay? Yeah, so these should be pretty quick in general. I hope for the ODPs to mostly be kind of incremental. So we talk about something, and then there's an ODP that lets you work with that. And increasingly, I think these will be more slam dunks because we're building on things that we've already done. So I don't think the steps will be as big going forward. Whereas in 224, in some cases, they were huge steps, right? Because it's new concepts. All right, so we left yesterday with this code that was allocating a bunch of nodes and linking them together, and we looked in GDB to play with that. So let's talk about memory leaks. So in general, when we malloc something, we'd like to free it. So in this case, I'm mallocing a struct node, and I'm freeing it, and I'm mallocing and freeing, mallocing and freeing. Okay, that's usually what you want to do. If you need to use the node throughout the entire program, then at the end of the program, you should free your memory. But sometimes you're making a temporary node to hold a value or something, and when you're leaving a function, you're done with that location in memory, go ahead and free it. Okay, if you don't do that, then while your program is running, potentially it keeps consuming more and more memory. Now on Linux, when your program exits, all that memory gets freed. So there's no harm done. But if you're writing something like a server that's really not going to exit until the machine gets shut down, and your server is running for months at a time, and it's consuming a few megabytes of memory every day, right? That's a problem. Or every hour, that's a big problem. And after a few weeks, you realize the server's crawling and nobody can get their pages, and it turns out you've got a memory leak. So finding these things can be tricky. So we have a program called valgrind that you can use to look for memory leaks. And it's very easy to use. So try for, well, it doesn't do anything, try for, but presumably it's a program that does something. If you want to run it through valgrind, just say valgrind space and then the command that you were going to type in, like try for. And it runs your program, and when your program exits, it gives you a little report. So here's the report on try for. It says heap summary, in use at exit, 0 bytes in 0 blocks. Heap is the area of the system where we get memory from when we call malloc. Total heap usage, 3 allocates, 3 frees, 48 bytes allocated. So remember, our struct node needed 16 bytes, an integer, 4 bytes of filler, and then 8 bytes of pointer. So we allocated 48 bytes by doing 3 allocates. We also did 3 frees. And here's what you want to see. All heap blocks were freed, no leaks are possible. If you get that message, your code is solid as far as memory management, at least for that run that you just did. So let's see what can go wrong. Well, let's just get rid of these. So I'll allocate 3 blocks, and I'm going to call them N1, N2, and N3. And I'll val grind them. And now it's telling me that I've got some leaks. So the summary is I got 48 bytes and 3 blocks in use at exit. So leak summary, definitely lost 48 bytes. Indirectly lost 0, possibly lost, still reachable. We'll see those in a second. But the punchline is there were 48 bytes of memory allocated when this program exited. Okay, since Unix frees memory once your program exits, it's not a problem, but it's telling you that there's something that you're not freeing. Okay, so it's telling you there's a glitch somewhere in your code, something you're not doing the housekeeping on. Now here's a more common scenario. We malloc a block of memory, we store it in this variable N1, we do some stuff, right? And then somewhere later on, we reuse this temporary variable N1 to point to another block of memory. Well, once we do this, we have no way of getting a hold of that first block of memory. We can never free it because we don't have a variable that points to that block of memory. I said N1 equals malloc in that first statement. N1 was a variable telling me where that block is in memory. As soon as I change N1, I've lost that block forever. I can't go back and free it now. Now if I had said N2 equals N1 and then changed the value of N1, I'd still have a reference to N1. I could still free it. But in this case, I've lost that block and there's nothing I can do at the exit of my program to free that memory. And that's a bit more of a severe error. So if I run val grind on this, it'll tell me, well, it's still definitely lost. That's not interesting. It'll tell me it's still definitely lost. Let's see if we can get something different. Well, that's annoying. This was much more fun the other day.
We can put something like if loop or like if statement but make it possibly lost.
It might.
Maybe it's just because you're not doing anything.
Maybe. Those and through this should still be reachable though.
Maybe you do like N1 and set N1 to be 34 and a free N1.
Maybe. Huh. Well, this is disappointing. I had something simple. It was basically 3 lines of code, but it was demonstrating things were still reachable. Well, let's ignore val grind for a moment, right? The idea here is that N1 at the point of when I'm exiting my program, N1 is still pointing to my first block of memory. I can still free it. N2 is pointing to my third block of memory. I can free that, but I don't have a pointer to my second block anymore. So I could free these. Right, but I'm still going to have one block that's been lost, which was that second block. So it knows that I did 3 allocates, I did 2 frees, and at exit I have 1 block left with 16 bytes in it. And if you like reading, you can add this switch, leak check equals full, and get a more detailed output. So here it's telling me where the malloc is and so on. So for PA2, you want to free all your memory when your program exits. You don't want any memory leaks. And I'll val grind your program, and it's a few points if you have a memory leak in there. So when you delete a node, you need to free memory. Okay, that one's really critical because you're using temporary variables. Once you exit your delete routine, probably those variables are gone. So you got to free it when you delete. And at the end of your program, before you exit the program, go through your entire linked list and free all the nodes. And you can do that with a similar routine to what you do in print, right? Start the sentinel, save it in a temporary, right? Free the sentinel, but save the address of the next node. Move to that next node, save the address of the next node, free the first node, and work your way all the way through to the end. And run val grind on it and make sure it says no leaks are possible. You can do that at the very end, right? It doesn't change any of the other code. So get all the other functions working, get your main program working, and so on, and then go ahead and add a routine to free the memory in the list. But don't get bogged down on it to where it stops you from getting the other pieces. All right, questions on that? Basically just malloc and free, use them in pairs. Testing 1, 2, 3. Okay, we're still good. So let's look at some of the algorithms again for doing linked list manipulation, but using the language of memory pointers, right? Pointers to structures, the things we're going to be doing, PA2 and the rest of the course. But let's look at these algorithms, and they'll probably look a little more natural than when we did this for PA1. So our sentinel is going to be a struct node star. I'm just going to call it list. And that points to the sentinel node, right, which always exists no matter what the list looks like. So you're going to initialize this with your init routine. And what does your init routine have to do? Return a pointer to a structure node. So how do you create a struct node out of thin air? Yeah, perfect. So make a temporary struct node pointer, set it equal to malloc size of struct node, right? That temporary pointer now has the address of a struct node. Set the next field to null, set the data field to something if you like, and return that pointer's value. So now init returns the address of a sentinel node, and I set list equal to that. List is effectively pointing to this sentinel. So I'll put my usual 42 in the data and null in the next field. So let's print. So print takes an argument which is a pointer to a struct node. That's the address of the sentinel, right? That's always the thing that we're passing around. It's the handle we're using to hold on to this list, right? All we have is the address of this first node, the sentinel. So what do we have to do in here? We need to look at the node that list is pointing to. So this is not going to be an int, it's going to be something like a struct node star. Let me just call it temp. So arg is the address of the sentinel. How do I find the address of this node here? Yeah. Perfect. So arg arrow next. That makes temp right here. So the body of our loop will do two things. We need to print the data field of this node. That's just temp arrow data. And then we need to move temp to point to the next node in the list. And we already did that with arg. That's just temp equals temp arrow next. That changes temp to here. And now we're going to print data temp, that's this number right here. We're going to set temp to temp arrow next. That changes temp to here. Are we done? No. We haven't printed this data value yet. So we still want to do this pair of instructions one more time. Print temp arrow data, that prints this number. Set temp equal to temp arrow next. Now temp is equal to null. And at this point we want to exit our loop. So we want to repeat these two statements until we get to the case where temp equals null. So this can just be a while temp is not null. So test your edge case. If all we have is a sentinel node, we're going to pass in arg, right? That's the address of the sentinel node. We're going to set temp equal to arg next. That's going to be null. Well, temp is not equal to null. We're going to exit this while loop right away. We're not going to print anything. And so we'll just print our new line at the end if we're printing our nodes side by side. And that's the end of our function. So all the stuff happens really just in this one while loop with a little bit of setup. Does that seem pretty clear? So what does a search look like? Almost the same thing. Same setup, right? Make a temp. Struct node star temp. And start with the first data node. And it'll be the same while structure. Instead of printing, we check the data value. So if temp data is equal to num, then we can say it's found. Otherwise, move down the list. If we find our node, we're going to return, we're not going to get to the end of our loop. So if we get to the end of our loop, it wasn't found. So we can just return that value. So a few things to note in here. Temp is a struct node star. It's a pointer to a struct node. We have no need to do a malloc here. If we were creating a node, we would say temp equals malloc, and then we'd get a new block of memory and temp would point to that. But we're not using temp to hold a new block of memory. We're using it to point to the nodes that are already in the list. So you could do temp equals malloc up here and then do temp equals list next, and your code will still work, but you're needlessly allocating a block, which you have to free at some point. So we're just using it as a pointer. Since it's going to take on values that already exist, we don't have to initialize temp to point to a new block. When we do this, temp takes on the address of a node. And the single variable temp, again, takes on, in a sense, the essence of all these different nodes. Right? First it corresponds to this block, and then this block, and then this block. And even though it's the same variable temp, it's pointing to different locations in memory. Those locations come from the next field of the previous block. And one more time, it can be confusing at first when you write something like this. Temp is this block right here, right? It's not actually a struct node, it's a pointer to it. So my list, I kind of draw an arrow here to say it's pointing to this, but I might as well just say, you know, this is the node list. But I really mean this is the node to which list is pointing. Okay, it's a slight change in wording, but when you start trying to do things like temp equals temp arrow next, you need to understand this is not a node in this lower section here, it's the address of a node. That's why we can say temp equals temp arrow next, because we're taking on this address. Yes. And if you do that, if you say temp equals temp arrow data and your data is 10, then when I come up here and I look at temp arrow next, right, or temp arrow data, it's going to say go to the address that temp is pointing to, which is 10, find a struct node there, pull off the data field or the next field. But when it tries to go to address 10, that's not an accessible block of memory, you'll get a seg fault. Okay, similarly, if you don't do this check to see if temp is null, if temp gets to the value of null and I try to use temp arrow data, guaranteed seg fault. Because it's saying go to memory location null, which is 0, and that's not accessible. So with our array, if you had a data value of 10 and you accidentally use that as a next, you get garbage, but you're usually pretty safe because element 10 exists. -1, sometimes it blows up, sometimes it doesn't. But here, if you're doing the wrong thing with your pointers, almost certainly you'll seg fault, which is good actually, because it tells you right where the problem is. If you run this in the debugger, when you get a seg fault, it'll tell you which line you were on. Which may or may not be where the problem was. In fact, it's probably not where the problem was. It probably came with something that happened a few instructions before. but it gives you a test case, and then you go through and you start single stepping and all of that stuff. Alright, so here's a list. It's got 3 data nodes, 100, 200, 300. Let's add 250 to it. So, exact same idea that we've been doing since day one. Start off looking at the previous node and the current node. Current node is the first data node. So initially, previous is going to be the sentinel. And see if you should insert before the current node. If not, move down. See if you should insert before the current node. If not, move down, see if you should insert before the current node. If you should, make a new node, have the previous node point to it, have the new node point to the current node. Okay, it's the same algorithm we were doing before, but the language is a little different. I'll call this list this time so you don't fall in love with arg. And I'll call this number. So I'll make a pair of struct node pointers, previous and current. And I want to begin with previous pointing to the sentinel, current pointing to the first data node. So previous, instead of setting it equal to 0, what do we set it equal to? What's the address of the sentinel? List. And what's current? The first data node. Previous arrow next. So now my picture looks like this. I always do that. There's got to be a way to turn that into a winning lottery number. Alright, so previous and current. So we're going to do a loop while something. We'll worry about the something later. So we want to compare the number we're adding to the current node's data. So if current data is bigger than number, insert between previous and current. We'll build a node, we'll insert it, we'll adjust the pointers, and then we'll return. Otherwise, if this is not where we want to insert, we need to move these pointers down. So previous equals current, current equals current arrow next, you got it. Is it starting to click? And that's the end of our while loop. So this will be previous, this will be current. We'll check current's data, 200 is not bigger than 250, so change previous to this, change current to what that points to. And now when we check current's data, it's 300, that is bigger than our number. We want to insert between previous and current. So temp so how do we get a new node? Malloc. So malloc some memory. It's not a bad idea to check temp and make sure it's not null, just in case you run out of memory. You're not going to run out of memory in this PA2 unless you type a whole lot of insert commands or you have a glitch. But in practice, we would check temp to see if it was null, and if it was, we know we're out of memory, and we would do something, return a particular value, halt and catch fire, whatever. But otherwise, temp is a new node, so we want to set its data value to number. So temp arrow data equals number. So here's our new temp. There's our 250. So how do we adjust pointers? Temp arrow next equals previous arrow next. So this is pointing to here. We could also have said temp arrow next equals current. Same thing. All right. And then what's the other change we have to make? Previous arrow next equals temp. And then just get out of here. So this is one of these things where writing it is generally a whole lot easier and clearer than reading it. Right, which is why you want to be able to write it from scratch. Because it'll make sense to you if you piece it together like this, you know, working with a picture, drawing in how the links change, writing code that corresponds to each of the changes that you want. If you write that from scratch, right, there's a good chance it's going to work. And if it doesn't work, what you want to be able to do is go through in the debugger and see that it's doing each of these things, and that each of these things that it's doing corresponds to the changes you wanted to make or the actions you wanted to take on the linked list. Right, so you got your linked list, you got your code, you got reality and GDB, and they should all mesh with each other. If your program's not working, there's a disconnect somewhere. And it could be, I wanted this to point here, but I wrote something that had this point to itself, right? Or it could be that, you know, I wrote these correctly and we're being invaded by aliens and GDB doesn't work anymore. But it's probably not that, okay? It's probably a disconnect between here and the code. So GDB will help you figure out, like, I wanted this to happen, but in fact, you know, this happened. All right, so if we get all the way to the end, so let me change my picture here. Let's say we're adding 350. Let me take a picture of that before I change it. Okay, let's say we're adding 350. So forget about these changes we made. So we looked at 300, and 300 was not bigger than 350. So we changed previous to be this node, and we changed current to be what this was pointing to, which was null. So current equals null. And now we don't want to check current's data because we'll seg fault. So this while condition can again be current is not equal to null. So if we come out here, we're at the end of the list. So we make a new node, so make new node. So do your malloc, set the data field to 350, and what do we adjust pointer wise? So yeah, both of those. So previous, say again? equals temp, right?
Yeah. Yeah.
So we want this, instead of being the end of the list, to point to our last node. And then, I thought you said it.
For here, we'll temp arrow next must
Yeah, temp arrow next is equal to null. That makes that the end of the list. Or we could have said temp arrow next equals current, which is also null. But we set it to null explicitly, and then return. So the steps are the same as in PA1, right? The syntax is different, but we're doing exactly the same algorithm, right? Para pointers start at the sentinel node after it, march through until the current node, which we were calling next in PA1, until that thing is not actually pointing to a node, it's null or my null. And in that case, add your node after the last node, which was previous. And if you get to a point where you want to insert between current and previous, go ahead and adjust the previous pointer to point to the new, set the new pointer to point to the current, and you're done. So last entry, delete. So delete 200. So we can do this one a little more succinctly. I'll leave off all the struct node declarations and so on. Previous is list, current is list, arrow next. So here's previous. Here's current. And if the current node's data is the field that we're trying to delete, the value we're trying to delete, then we want to adjust pointers. So what are the 2 pointer changes? Well, there's 1 pointer change. So we want to delete current from the linked list.
previous arrow next is equal to current.
Take the previous node's next pointer, set it to whatever the current node's next pointer is, so that this points to that following node. Now, procedurally, that 100 node has been removed from the linked list. When we get to the node right before it, the next node's going to be the one after it. We're never going to encounter that 100. So it's been deleted from the list. And then you got to do one more thing so you don't have a memory leak. Free it. So here it would be free current. And then return. Don't do those in the different order. We need to use current next in order to set previous next. If you free current first, current next can be corrupt. Right? Once you free current, you're not allowed to use any of the fields that current is pointing to. Once you free it, it's done until you give current a new value. So if I want to use current next, do that before you free. Now if I copy current next into a temporary variable, I can free current, and then I can set previous next equal to that temporary. That's fine. It's not the value of this that's sacred, it's current itself is sacred. Right? Once that's freed, it's gone. All right, if the number that we're looking to delete was not the current node's data, then we have to move down the list, and that's the same drill as before. Previous equals current, and current equals whatever it points to. And this all goes in a while loop. And it's the same condition as before. We're going to stop while current is null. So while current is not equal to null, we do that loop. If we run out of nodes, say we're deleting 400, we'll eventually get to the point where this is current and next is null. And you know that your number wasn't in the list. But if you search for your number before you do your delete, you'll never get this case where you come out of the loop and you haven't found your number. So inside delete, if you want, you can call search, and if the number is not found, return right away. If it is found, you're guaranteed that this condition is eventually going to be true. If you don't want to do that, you can just put this in a while loop until current's null. If current gets to be null, you know your number wasn't found. And if you're deleting the last node, this should have been previous and current. If you're deleting the last node, previous will be this 200, current will be the 300. And if that's where the numbers equal, what are you going to do? You're going to set previous next equal to current next. Well, if current next is null, then that just copies that null into here. And that effectively deletes this node. Because now when you're following your nodes, once you get to this node, that says that's the end of the list. You're never going to encounter that. So in any case, this is going to do the right thing. And if you're deleting the first node, and this is previous and current, previous next will be current next, and it'll skip over that. So there's no edge cases for deleting if you know the node's in there to begin with. Sorry, I started using next over here. I shouldn't have done that. Changed my variable on you. All right, questions about that? That's all of PA2. That's the whole thing, right? I'm guessing if you sit down and you work on this one night, you can probably finish it. But don't make that night next Thursday. but pick a time when you feel like you can spend a few hours on this and really dig into it. Okay, this works better the more you immerse yourself in it up to a point. Right, working on it for 5 minutes, get confused, go away, come back, isn't going to get it. You got to get some traction going. Okay, but if you sit down and you work on this stuff for a couple of hours maybe, right, you should really be able to sink your teeth into it and get big chunks of it done. At some point, right, it's important to step back. If it's really frustrating, if you're spinning in circles in your head, if nothing's making sense, if you're forgetting what an integer is, right, then it's obviously time to take a break. Okay, so you don't necessarily want to just stay up all night working on something if you're not feeling like you're being productive. But this is an area where it can actually help to really kind of immerse yourself. Right? Get some good music, some good energy drink or whatever you like to work with, and plow into it. Right? And when you're halfway through writing this stuff, sometimes it's really painful to leave. Because you come back to it and you got to remember everything that you were doing, and no matter how much you commented and how many pictures, you got to come back up to speed. Right? I'll warn you, this is where programmers find themselves looking at the sunrise when they weren't planning to. They're like, I'll be home in a few minutes, at 7 o'clock at night, and the next thing they know, the sun's coming up. Right? So that's a bit of what you're in for if you're going down this route. But it's a good thing, by and large. All right, so tomorrow we'll talk about questions. So if you start working on this stuff, right, bring questions tomorrow. We'll talk about some variations on this, doubly linked lists, circular linked lists. And I want to look at what happens if we don't have a sentinel, just because I think it helps illustrate some of what's going on with the sentinel. So we'll look at some algorithms for that. And if we finish early, we'll probably start on the next topic, which is going to be stacks and queues. And that's what we'll focus on next week. All right, so I will see you tomorrow.